we were considering the definition of a grammar. The grammar consists of 4 components. G is equal to NT P S, where N is the set of non-terminals and T is the set of terminals, P is the set of production rules, and S is the start symbol. We consider 4 types of grammar: type 0, type 1, type 2 and type 3. If the rule is of the form U goes to V, then the application of a rule means if you have a sentential form alpha U beta, then you replace U with V, then you get alpha V beta. This means from alpha U beta you directly derive alpha V beta. And then if you derive something, say from alpha naught in alpha n from alpha naught in n steps, you denote it by alpha naught derives alpha n, and the language generated by the grammar is denoted by LG, and it is given by W. W belongs to T star. It is a set of terminal string derivable from the start symbol. This is the way the language generated by the grammar is defined. Let us consider some examples. Consider example 1. The non-terminal the grammar has a non-terminal S, only one non-terminal. The terminal symbols are A and B, and you have the set of productions. I will number them because the first rule is S goes to ASB, the second rule is S goes to AB, and S of course is the start symbol. There is only one non-terminal in this example, and that happens to be the start symbol. Now what is the language generated by this grammar? Let us derive some strings and see. Any terminal string derivable from the start symbol belongs to the language generated by the grammar. So let us see what sort of terminal strings are derivable in this grammar. So look at this. Using the second rule, starting from the start symbol, using rule 2 alone, you will get AB. So AB is a string which belongs to the language generated. So I can say AB belongs to L of G. On the other hand, you can say S, you can apply rule 1 and then get A, S, B, and then from this S you can derive using rule 2. S will be replaced by AB, this B will occur here, this A will occur here. So AA, BB is a terminal string which is generated by the grammar. So you have A squared, B squared belonging to LG. AA, BB can represent as A squared, B squared. And then look at this. Use rule 1 first, you get ASB. Then again use rule again, rule 1 again. So you will get A, this S is replaced by ASB, then this B will come here. So you have AA, SB, BB, and then use rule 2, you will get AA, AB, S is replaced by AB, then you get BB. This is again another terminal string derivable, and it belongs to the language generated. So you have A cubed, B cubed belonging to LG. Now you see the pattern. Whenever you apply rule 1, 1A is generated, 1B is generated. In between you have the S, and finally when you replace that S by AB, another AB is generated. So, at any step you have equal number of A's and equal number of B's, and not only that, first A's occur first and then B's occur next. So, the language generated consists of strings of the form L of G is A power n, B power n, n greater than or equal to 1. Strings of the form A power n, B power n, number of A's followed by an equal number of B's will be generated by this grammar. Okay. And to generate A power n, B power n, you will be applying rule 1 n minus 1 times and rule 2 once. And in general, the derivation tree, take A cubed, B cubed, the derivation tree will be like this: S, A, S, B, A, S, B, A, B. The derivation tree will, in a derivation tree, in a context free grammar or type 2, this is a type 2 grammar because see that on the left hand side you have a single non-terminal, on the right hand side you have a string. So, this is type 2 or context free grammar. In general, the rules when you apply an internal node, suppose you have a rule A goes to B1, B2, Bm. The internal node labeled A, there will be a tree, and somewhere the internal node will be labeled A, and it will have sons B1, B2, Bm. The derivation tree, it will be represented like this. The leaves will have terminal symbols, and if you read out the leaves from left to right, you get the string generated. From left to right, if you read out the labels of the leaves, A, B, 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 that is the string generated. That is called the result of the tree. It is called the result of the tree, or the terminal string generated by the tree. So, this is one example. Consider some more examples. Consider another example. Here again there is only one non-terminal S, which happens to be the start symbol. There are 3 terminal symbols A, B, C, and the production rules are S goes to A, S, A. Second rule is S goes to B, S, B. Third rule is S goes to C. There are 3 rules now. S goes to A, S, A, S goes to B, S, B, and S goes to C. Now, what is the language generated by this grammar? Let us see how strings are derived in this grammar. Starting from S, you apply rule 3, you get C, right. So, C belongs to L of G. And then starting from S, apply rule 1, you will get A, S, A. Then you apply rule 3, you get A, C, A. Okay. So, A, C, A will belong to L of G. Now, starting from S, if you apply rule 2, you will get B, S, B, and then if you apply rule 3, you will get B, C, B. So, B, C, B will belong to the language. Now, starting from S, you apply rule 1, then apply rule 2, then apply rule 3, you get A, B, C, B, A. So, A, B, C, B, A will belong to the language. Now, what sort of strings can be derived in this grammar? So, first you can apply rule 1 or rule 2. When you generate using rule 1, one A will be generated this side, another A will be generated this side. Then you can use rule 1 again or rule 2. One B will be generated here, one B will be generated this side, or one A will be generated and one A will be generated. Finally, you have to end up the derivation with S goes to C. Once you apply that S goes to C, you cannot proceed further. You have to stop the derivation at that stage. But before applying rule 3, rule 1 and 2 you can apply again and again in any order. Either apply 1 or 2 and 2 and 1 or 1, 1, 2, any order you can apply. But whenever you apply rule 1, one A will be generated this side, one A will be generated this side. When you apply rule 2, one B will be generated this side, one B will be generated that side. So, you can see that any string generated, for example, a string of the form A, B, B, A, B, some string, some sequence of A's and B's followed by C, then when this B is generated, this side also he must get a B, right. So, this side what will be the string generated? B, A, B, B, A. The reversal of this will be generated this side. So, such a string will belong to the language generated. So, LG consists of strings of the form W, C, W, R, where W belongs to A, comma, B star. W is a string of A's and B's, a string of A's and B's, then C, then the reversal of the first portion will be generated. Now, by W, if W is a string of the form A1, A2, AN, WR is the reversal of W, reversal of W, and that is nothing but AN, AN minus 1, A2, A1. This is called the reversal of this string. So, the language generated by this grammar has the strings will be of the form WC, WR. Okay. And if you take a derivation tree, S, A, S, A, B, S, B, C, something like that for A, B, C, B, A. So, you can see that when S is replaced, one A is here, one A is here, one again when this X is expanded, B, S, B, one B is here, one B is here, then S is replaced by C. The result is you have to read the leaves from left to right, A, B, C, B, A. So, this is another example. Both the examples which we considered here are context free or type 2. And one more thing, on the right hand side you see that there is only one non-terminal. So, actually it is not, it is a slightly restricted version of a context free grammar. In the definition of context free grammar or type 2 grammar, on the right hand side you can have any string, right. But in these two examples which you have considered, on the right hand side you are having along with the terminal symbols only one non-terminal. So, it is slightly restricted version of a context free grammar. Such a grammar is called a linear grammar. Linear grammar. And the language generated is a linear language. The condition for a linear grammar is RHS has at most one non-terminal. You can have just terminals alone. So, after considering these two, we will consider one more example of a context free grammar, slightly more general than this. Then some type 3 grammars we will consider. These do not belong to type 3. The reason is type 3, the right hand side should be a terminal symbol followed by a non-terminal. Here you are having a terminal symbol followed by a non-terminal, then another terminal symbol. So, these two will not belong to type 3 class, they are slightly higher, type 2. Okay. Let us consider one more one, which is a variation of this, but you see that lot of different strings can be generated. There is only one non-terminal S, there is only one non-terminal S, two terminal symbols A and B. There are two rules, S goes to A, S goes to B, then there is one more rule, S goes to SS. One more rule is there, this S goes to SS. With this additional rule, what is the language generated? What types of strings are generated by the grammar? Start from, with these two rules alone, you see that you can generate strings of the form A power n, B power n. You are having one additional rule, S goes to SS. Now, this rule, see that there are two non-terminals on the right hand side. So, this is not a linear grammar, it is higher than that. This is a type 2 grammar because left hand side there is only one non-terminal, right hand side you have a string. So, it is type 2, but it is not linear, right. Now, let us derive some strings and see. S goes to SS, of course all A power n, B power n can be derived by the first two rules alone. S goes to SS, then from the first S you derive AB, from the second S also you derive AB. So, AB can be derived, which cannot be derived with the first two rules alone, right. Similarly, you can see that AB can be derived, AB, 4 ABs can be derived and so on. More than that, you can derive something like this, S goes to SS, S goes to ASB, AB, this S is replaced by ASB, this is replaced by AB. Now, this S is replaced by SS. Now, each one of this SS you can replace by AB. So, A, AB, AB, B, AB. Such a string can be generated by the grammar. How do you describe the language generated by this? Let us consider the derivation tree for this. It will be S goes to SS, this goes to AB, then this goes to ASB, this goes to SS, then AB, the derivation tree for this derivation is that. So, please note that from going to from this sentential form to this sentential form, 2 steps are involved. That is why I have put star here. From this to this, only 1 step is involved, is rewritten as SS. Going from this to this, 2 steps are involved. S is replaced by AB, S is replaced by AB. The derivation is sequential here. At any step, you are using only one rule. The order is immaterial. It has to follow a proper order, but which one you replace first is immaterial. But if you use a leftmost derivation, you must replace the leftmost non-terminal. Okay. So, the derivation tree looks like that. Now, this is the father of these, and these 3 are the sons. This is an ancestor of this. This is a descendant. All those terminologies. And this, if you look at this, this is a subtree. This is a subtree. So, these definitions, subtree, father, sons, ancestor, descendant, whichever terminology you use for trees, they are also used here. Okay. And the internal nodes have non-terminals as their labels, leaves have terminals, and if you read out the labels of the leaves from left to right, you get the string generated, and that is called the result of the tree. Okay. Now, how can you describe precisely what is LG here? What is LG here? You must realize that when you use rule 3, you are generating only SS. Then, when you use rule 1 or rule 2, you generate 1A and 1B. Whether you use rule 1 or 2, 1A will be generated, 1B will be generated. So, the resultant string will always have equal number of A's and equal number of B's. Something more also. You cannot generate BA. Can you generate BA with this? You cannot generate BA with this. So, the resultant string generated in the grammar will have equal number of A's and B's. For example, here you have 4 A's and 4 B's. Not only that, there is some more feature. What is that feature? If you look at A as a left parenthesis and we look at B as the right parenthesis, what does that mean? It is a well balanced string of parentheses. If you look at A as a left parenthesis and if you look at B as the right parenthesis, this string will be right. So, any well formed string of parentheses will be generated by this grammar. Okay. So, the language generated is LG consists of well formed strings of parentheses. If you look at A as the left parenthesis and B as the right parenthesis. Okay. This particular grammar and this particular language has certain special features. We will learn about that as we move. There is a difference between this and that, such linear grammar. Not only that, I will again give one more example. There is a basic difference between this and other type. So, this is called in Dijkset. This particular language, well formed strings of parentheses, is called a Dijkset. Okay. Now I will modify this grammar again a little bit. Now you tell me what is the language entity. There are only two terminal symbols. The rules are S goes to ASB, S goes to AB, and two more rules. Some S1 goes to S1, S1 goes to, there are two non-terminals. The rules are like this, four rules are there. S1 goes to S1, S1 goes to epsilon, S goes to ASB, S goes to AB. Now S1 is the start symbol. What sort of strings can be derived in this grammar? Now you can have S1 derives epsilon, right? You can use this alone. So epsilon belongs to LG. In the previous three examples, the language did not generate the empty string. Empty string cannot be generated in the previous three examples which we consider. Whereas in this example you find that epsilon is generated by this. Then I can use S1. Now replace this S1 by epsilon. So you get S. Then from this S you can generate A power n, B power n. Okay, or start with S1, one S I can have, and again from this S1 another S I can generate. Then I can make this S1 go to epsilon. So now two S's I have. From one of the S's I generate A power n1, B power n1 by the usual method, by many steps. Then from the other S I can generate A power n1, B power n1, A power n2, B power n2. From the second S I am generating A power n2, B power n2. Okay. This sort of a thing I can do any number of times. So in general you can derive strings of the form A power n1, B power n1, A power n2, B power n2, A power n3, B power n3, A power nk, B power nk. Strings of the form A power n1, B power n1, A power n2, B power n2, like that can be generated by this grammar. Okay. The derivation tree will be like this. From S1 you generate S1. From this you can generate A power n1, B power n1. From this one again another S1. From this you can generate A power n2, B power n2. Then from this again another S1, like that. Finally the S1 goes to epsilon. the derivation tree will be of this form. This is also, I mean, equal number of A's, equal number of B's. What is the basic difference between that and this? There is no nesting there. Then there is nesting here. See, within this left parenthesis and right parenthesis you are having this. That sort of a nesting is not possible here. You have A power n1, B power n1, A power n2, B power n2, like that, but no nesting is there. See the difference. Okay. What is the language generated by this grammar? It has strings of the form. Can you express it in a simplified form? Suppose I denote by L, A power n, B power n, n greater than or equal to 1. The first example which we considered. What is the language generated by the fourth grammar? I will put it as LG4. What is the connection between this and this? You have studied set operations on sigma star. So, that is L star, right? The clean closure of L. What is L star? By our definition, L star will be L0 union L1 union L2 etc. Right? What is L0? L0 is just epsilon. Epsilon can be generated. L1 is just A power n, L itself. L2 will be, L2 will have strings of the form A power n1, B power n1, A power n2, B power n2. Lk will have strings of the form A power n1, B power n1 etc. So, the language generated is L star here. This is not same as this. Here please note that there is nesting. So, there is basically a sort of a difference between this grammar and this grammar. I will slightly put it more explicit. Suppose I want to derive A power n1 B, this string. I want to derive this string. How do I go about doing this? Suppose I use a leftmost derivation. Then afterwards from this I can derive A power n1 B power n1, right? Then I use S1. Then from this S, A power n2 B power n2 S1 and so on. So, you will find that any string you can derive in such a way using a leftmost derivation in any sentential form. You need to have at most 2 non-terminals. Maximum number of non-terminals which will be occurring in any sentential form is 2 if you use a leftmost derivation. In this example I have derived in such a way you have 3 here, but you could have done with 2. First derive the A power n B power from S, then expand the S1. We can proceed like that. So, you can have a derivation in which every step you will have 1 or 2 non-terminals only, not more than that. Whereas, in this grammar, as the length of the string increases and also as the nesting increases, the number of S's in any sentential form will keep on increasing. For example, there may be a string which you cannot derive with 4 non-terminals. You may require 5. The level of nesting is 5. You may require 5 S's at one stage. Similarly, there may be a string, there is a string which will require at least 10 non-terminals in one step. As the nesting and the length of the string increases, the number of non-terminals in any sentential form you cannot bind it. Okay, it is not bound. So this is called this sort of a language is called derivation bounded. And this sort of a thing also it is called the language of finite index. This grammar and this language Dijkset it's not a finite index. This is a major result. Actually, we will consider more about it later. So it belongs to a different class. Now, having done that, so far what we have done is we have taken grammars and then tried to find the language generated by the grammar. That is rather simple exercise. The real way you will tackle is you have to find the grammar when the language is given. That is what is required in compilers. You try to define a new programming language or a new programming package or something like that. Then you want to write the compiler for that. So you have to capture the whole feature of that language using a grammar. So given the language, you will try to find the grammar. That is the real problem which you have to tackle. So let me just change, let us consider one or two examples for that. For example, this well formed string of parentheses we have considered with this. Suppose I have to find all well formed strings using this. Two types of parentheses I want to have. Still it has to be well formed. What grammar will generate this? You must have this S goes to S for nesting purpose. That should be there. Then when you generate one left parenthesis, you must generate the right parenthesis. In between, you must allow for nesting. So S goes to this should be there, and terminate also you should have this, and similarly for the other one also you should have. So S goes to this and S goes to. So with this you can generate square parenthesis, square brackets, and here ordinary parenthesis you can generate, and with the S you can generate S goes to SS and have any sort of combination. But whenever a left square bracket is generated, a right bracket will be generated, matching one will be generated. So it will always generate only well formed strings of parenthesis. If you want to have another one also, you must have two more rules. That's all. So this is actually, this is called Dijkset on 2 letters. This is called Dijkset on 4 letters. Generally you have Dijkset on 2n letters. N types of parentheses you have. Dijkset on 2n letters. Two n symbols. Consider a grammar which will generate Fortran identifiers. What is the structure of a Fortran identifier? It can have up to 6 symbols. First one will be a letter. Second to 6 it can be digit or a symbol, a letter. Okay. So we will use letters letters, I would mean, I use capital only, push, you can change it digit. Digit denotes 0 to 9, right. So, how can you generate all Fortran identifiers? You can have a non-terminal and all I will write later. S goes to letter S. Okay. You can have a rule like this. Letter should take all possibilities A to Z. Okay. That means 26 rules will be there. And then S1 goes to epsilon you can have, which would mean you just have a identifier A, C, X like that. Okay. Now you can have an identifier with 2 letters, second one can be a digit also, you should allow for that. So what do? You allow S1 goes to letter R digit S2. So after generating one letter, you can generate another letter or a digit. So there will be, actually I am writing like this, it represents 36 rules, right. Then you can stop at that stage. S2 goes to epsilon, or you can continue, you can have up to 6 letters, up to 6 symbols. The first one will be a letter, second to sixth one it can be a letter or a digit. So S2 goes to epsilon will terminate with the second symbol. If you want to use one more symbol, S2 goes to letter digit S3, and then S3 will go to epsilon. This will generate up to 3 symbols. This will generate up to 3 symbols. If you want to generate the 4th symbol, S3 goes to letter digit S4, S4 goes to epsilon. So this is one symbol, 2, 3, 4, up to 4 symbols you can generate like that. To generate the 5th one, then to generate the 6th one, or I can combine this. Actually this represents 26 rules, this represents 36 rules, you must remember that. So you can have a grammar which will generate all Fortran identifiers. You can express it as a regular expression, this which I will learn in due course. And what type of a grammar is this? Look at this and tell me what type of a grammar is this. You can see that the left hand side is a single non-terminal. The right hand side has one symbol followed by a non-terminal. It can be a digit or a letter followed by a non-terminal, or S goes to epsilon. This is the definition of type 3 grammar which you have considered. So this is a type 3 grammar or a regular grammar. So the non-terminals we have used here are S, comma S1 to S5. Terminal symbols are letters union digit. Now going back to type 3, look at this grammar. Let us consider one more example. The grammar has 4 rules. S goes to AS, S goes to BS, there is only one non-terminal S and 2 terminal symbols A and B. There are 4 rules. S goes to AS, S goes to BS, S goes to A, S goes to B. What is the language generated? What type of a grammar is this? On the left hand side you are having a single non-terminal. On the right hand side you are having a terminal symbol followed by a non-terminal or just a terminal symbol. So this is a type 3 grammar. And what sort of strings will be generated in this grammar? For example, I can generate A alone, I can generate B alone, I can generate AB, I can generate AA, I can generate BA, I can generate BB. All 4 strings of length 2 or can be generated. In fact, you can see that any string of A's and B's can be generated by this grammar, any sequence. Suppose I have something like A, B, B, A, B, A, B, something like that. If I want to generate, whenever I want to generate A, I use rule 1. Then rule 2, rule 2, rule 1, rule 2, rule 1. Then ending up I have to use rule 4 for B, rule 3 for A. The derivation tree will be like this. For this, S goes to A, S, B, S, B, S. It has a special structure, you can see that. A, S, A, B, B, A, B, S, A, B, B, A, B, A, S. The derivation tree will look like this. So any string of A's and B's will be generated. So in this case, LG is, this is example 5. LG will be sigma is AB. Any string of A's, but epsilon cannot be generated by this. Now instead of these 2 rules, I just have S goes to epsilon, then I can generate epsilon also. I can generate any string of A's and B's. So if I replace the 2 rules by S goes to epsilon, the language generated will be sigma star, where sigma is AB. Any string of A's and B's can be generated. Okay. Type 3 is the simplest form of a grammar, regular grammar, and it is used to describe the like identifiers, integers. Try to generate integers, other things using type 3 grammar, decimals and so on. We can do that. So the idea of type 3 grammar is very much used in lexical analysis, where you have to recognize the tokens. Tokens are recognized as keywords or identifiers or operators or equal to operator and so on, and they are put in symbol tables or constant table, and so there will be a pointer and so on. We will spend some time on that later on.